Hi, so welcome back, everybody. So we're talking about system on chip, but right now we're still kind of going through a little bit of review of things. We have our first kind of assignment, which is really designed to help me see where you're all at and to also get all of you to kind of remember how to build and design some of these components. And what you're building is basically kind of a game off of them. And we talked a little bit about that game last time. And we also mentioned that there was the ability for us to make kind of pseudo-random numbers and things like that. So given where everybody was at, I figured it, and there were some questions after from a couple people about, how do I make a synthesizable random number generator? Because you can obviously, for simulation purposes, using the $URAND, right? Or URAND underscore range, and you can give a min max, is a reasonable way to get a number when you're doing simulation. But URAND and its variants like underscore range are not synthesizable as a general rule. Somebody could make a library to do it, but in general it's not, because it's actually not a trivial thing to build a random number generator. And so what I wanted to do today was to talk a little bit about a couple different ways that we can do parts of these components and kind of break it up. So I wanted to talk a little bit about random number generation at the start and do a little more detail, and then spend the rest of the class talking about some of these fundamental components and some of the things you can take from the code that's available from the book. So there's some book stuff in the chapter that you can actually use to break this project up into a fairly simple project, but you have to understand them. So we'll do a little bit of talking. I'm going to first off kind of go through a board coverage here of stuff you need to understand about both, right? So, and then we'll go through doing the code. The main reason I'm going to do it all on the board first and then the code, even though it really would be kind of nice to do what you need to know about random number generation, show the random, and vice versa, is it's just a pain in the butt to pull the screen up and down, and once it's projecting, it's really hard to read. And when you turn the projector off, the warm-up time is a pain. So I'm going to do all the theory first, and then all the code. It's basically the set down. So let's talk about random number generation first. So we talked briefly about last time, where I just mentioned some stuff with linear feedback registers and pseudo-random sequences. So let me ask you, when is a random number sequence, when does it actually have to be random? Like truly random.
Encryption.
So that would be a great example, right? So cryptography, crypto stuff, very high. Any associated thing with crypto. So there's some communication algorithms and other stuff that rely upon some type of a random sequence. So that's very important, right? If in any way you don't get a true random sequence, you use any of these pseudo-random ones, you will get a complete garbage result. So for instance, we're going to talk today, and I'm going to give you a very short little piece of code for a 168-bit sequence, right? Generator that'll generate pseudo-random sequences, linear feedback shift register stuff, LFSR, right? And that repeat on that will be, it won't repeat again to 2 to the 168th cycles. Right? Now, if you think about that, 2 to the 168th, this sounds really impressive, right? I mean, somewhere around 2 to the 63rd is like 5,000 years. So, I'm 2 to the 100th past that. So, our sun will be a lump of coal in the sky by the time this thing repeats again, right, at the speeds at which our systems are running. So that sounds like it should be more than enough for anybody, right? Yeah, the problem is not when does it repeat again, it's when does it become predictable, right? And is everything uniform? So I can, even if everything's perfectly in its proper scaling, so you can run it for a large amount of time and you take a look at the random numbers and see if the distribution, your histogram matches the distribution. in theory, the histogram of values produced should converge to the probability distribution. Right? It'll never be perfect, but it should converge to in the limit. Right? Now, even if it matches that probability distribution, if the next one in sequence is predictable after a certain point, you're in trouble. It was shown for these LFSR and the pseudo-random type ones, even if I don't know what you're doing, if it's of length n, that if you give me 2 to the n consecutive points, I can tell you what the next one is, even if I don't know what your algorithm is. All right? So that means, in this case, I need, 336 data points. And it becomes predictable. So it won't repeat again for billions of years, right? But, even though it looks really crazy to the human eye, it becomes repeatable and predictable after, or predictable, not repeatable, after a short period of time. It's fairly decent, uniform and all kinds of other stuff. So crypto, it would totally stink for. So you should never, ever, ever use one of these pseudo-randomy things if you really care about them. There are some very fancy ones, but even if you use like a Mersenne twister, right, which is a very complicated method for generating these, and it won't repeat again for 2 to the 600th and something, right? A really, really crazy number that's out there. The fact that it is actually not truly random reduces it enough that it becomes crackable under a much less condition. So crypto, really, really important, right? You definitely do not want to use the pseudo-random stuff for that. Anything else?
There are 2 cases I can think of.
Okay.
So first in some algorithms like quicksort in partition, you need like universal random access.
Yeah.
If it's not, we're not guaranteed n log n.
So there are some algorithms whose fundamental properties rely on this. And it turns out that random algorithms actually are somewhat more powerful in some sense, right? And so, for instance, randomized quicksort is actually better than just quicksort. I put a little hedge on there, right? Some people argue on it. But the nice thing about the randomized one is that there is no default case you can give me that will break it. And if I run mine a second time, it sure ain't going to break it a second time, right? So since it's n log n and the average for both quicksort and randomized quicksort, the randomized quicksort just doesn't have an easily breakable case to do. So randomized algorithms have some nice properties to them. But if it's predictable, right? Anytime it's predictable, I can now make bad cases for it that will just always give it a problem. So algorithm's important. What's your other one?
We want to perform full functional coverage. You need random sequence generator.
Or actually any of your test cases that are doing, right? So I may or may not be trying for functional coverage. There's all kinds of stuff I could do, but whenever I'm testing things in general, I really want random numbers. Right? So you certainly don't want to do any of these fake things, but that's why we give you a function you ran that actually has, if they do their job right, a decent one. You'll notice that there's, in addition to the urandom, there's also random. And some people ask, what's the difference? Random stinks. That's the difference. So you should never use it. So random was the original, right? And the urandom actually was put in to fix the problems because it wasn't actually random. So when you went to start doing this, take a look at functional coverage and other areas that you would select within your test, random did not work well. So it still exists for legacy, but it's deprecated. And it's deprecated because of exactly this, it stinks at it. There's one other kind of interesting one that should stand out on this, which is gambling. So this is one of those interesting ones to mention, because in states where gambling is legal, and this is probably true with countries, but I just know with states, like for instance Nevada, it is illegal to use anything other than a true random number generator inside digital slot machines. So if you were to manufacture one using a pseudo-random number, you are now legally responsible. That is a criminal charge, right? This is one of those cases where your design hits legal. And the reason why it hits legal is it's so much money. Because if you do pseudo-random, that pseudo-random could either be skewed to break the bank or break the customer, either side, right? So depending on which way that pseudo is skewed, it can actually cause an advantage or disadvantage to one side or the other. A lot of money is passing hands on here, so in essence, you're stealing from somebody, right? Now, I personally think gambling is a dumb idea, right? You can think whatever you want. I'm just going to advocate that one. I think it's a foolish waste of your money anyway, but it is a case where legal comes in and says, hey, look, you're not allowed to do something that's going to be unfair advantage. Potentially you could have other ones too, but it's worth mentioning this, and I really want to mention that one just because of the legal constraints that are in. Yes, gentlemen.
Apparently there was an article
Was there?
about an Austrian casino company that used a predictable pseudo-random number generator, and people were taking advantage of it to make money.
Yes. So, yeah, that's a good thing for those under. So an Austrian company that got hit by this. There's also, if you look up, it's an older reference, but there's actually a guy at one of the companies that generated the slot machine, digital slot machines for Las Vegas, that had, since he knew the predictable algorithm, right, that was in it, this was a while back, he was able to actually skew it and use it to break the bank, and that's how they found out it was him, because he just got too greedy, he took too much money.
How are you gonna do that? Don't be dumb.
Yeah, I guess if you're gonna be illegal, be smart illegal. It's kind of there have been a number of them. So there was also another one who did this. This was another early on one where there was an internal switch that used a magnet, and the person put a magnet in their foot, in their shoe, so that they could put their foot by the side of the machine, and it flipped which a different set of, was it using a truly random or a non-random,
That's pretty scary.
right? So you could just kind of sit there and kind of kick their foot over, and it triggered it. But again, it was one of those cases they won enough that people are like, this is not too likely. So it really does actually really kind of hit on these areas, so it's important. So this is just my caveat on those. Okay. There are a variety of different ones that are in here. So there are what are called PRBS, pseudo-random binary sequence. So you can look these up. These are algorithms. The linear feedback, state registers, LFSRs that are in. These ones, I'm going to just categorize them in the same thing, because what these are is you've got a sequence of registers that are fed straight in between, all the way down. And then the new bit coming in, so it just shifts straight down. Right? The new bit that's coming into it is the product of some function, which is almost always XOR. Right? And pull-ins from, these are called taps. And pull in from certain of the taps. And then what they do is they try to pick what is the tap locations that will guarantee the maximal repeat. How long till it repeats something. Now, this is linear because exclusive OR and whatever they're calculating in here is actually a linear function that's on it. It's reversible and all other kinds of nice stuff. So in theory, if you know my taps and you know the initial n bits, you know everything forever. Right? So that's why it needs the 2N to do it. They use the first N, you can kind of predict which one it is, and the second N, you now know the state, and off you go. But anyway, so that's kind of where these ones are going. Does that make sense? Right? This format here is called the Fibonacci format. Fibonacci. Right? So if you've heard of Fibonacci numbers and all that, so it's named after that same mathematician that's on. And he does them this way. There's a second format, right? So he just takes the ones and they flow this way, called the Galois. Named after another very famous mathematician that takes this format and you reverse the order, and the function, instead of being just kind of being used to calculate this one, this is typically done as a series, like let's say we take these, let's say there was 4 taps coming in, which is pretty typical. The function typically in a Fibonacci one is going to look like exclusive OR, and then exclusive OR the next bit in, and out it goes. All right, so that's a pretty typical Fibonacci setup where these weights are at some locations, whatever, at location A, B, C, and D. And the way that you go to Galois, like I said, you reverse the direction of them, and then you put the XOR coming in. If this was location A that it's feeding out, you're actually backwardsing these. So you're going to take this, and it comes from its previous stage, and from this last one that feeds in, and just basically just inverts them. So you'll get an XOR between each one. So it's kind of, do you want one big one to calculate, or do you want them in between? So those are the two forms, and both of these end up being maximal for their area and everything else. So it's kind of nice to convert between the two. And people make arguments for one versus the other. I'm not going to sweat it because we're not that worried about the performance areas on it. It's not that hard. Where these taps are, you can actually just search for them. Xilinx actually has the first 168 length strings, all the tap locations categorized for 1 through 168, or 4 through 168, whatever. Right. So you can just pull their taps off. We're going to do the 168. None of these require more than 4 taps. It's kind of the fun thing about it. It's actually a very simple routine form. So that's kind of 2 of the big ones that come in. There's another one of these that is, has anybody heard of cellular automata? There's another, I won't go too far into this one. There's these things called cellular automata shift register ones that if you've ever looked at them, they generate these chaos patterns. So there's certain, like anybody heard of the Game of Life? You see these little shapes form out and stuff like that. The Game of Life is an example of a cellular automata. So it turns out that you can make these cellular automata simulations and you can pull a row out of them. And since each one is fairly complicated on its calculation, you can actually get some interesting factors. Right? So another one uses cellular automata to calculate and you pull a row out from them. That's another whole big family of them. And then there are what are called hybrid methods, where you pick like a 36-bit version of this and a 43-bit version of this, and then you dynamically mix them, and you'll get cool features of both. Now, as cool and as complicated as anybody makes them, they're still in this you're doomed zone, right? So, you'll find ones that may work, and there's a couple free ones that are out there that you can try. They tend to be complicated in how they write them, so that's why I'm giving you a simple one that just introduces you to the basic idea. And for a little game for us that you just have to do for a demo for next week type of a thing, I don't see a reason to kill yourself. So we'll just do one, we'll actually do this Fibonacci format here, because it's really simple to make a sequence of these and then draw caps and run it into a giant XOR. Because these cascading XORs is identical to one big XOR. So I can write this whole thing in one line of code, and this is trivial, it's just a concatenation of the first half of every string except the last one. You just take all those and concatenate this function at the end of it. That's really, really simple. And classically, you output that bit. Although in theory, you could grab, the first, if you wanted like 12 bits of something, you could just grab the first 12 bits here too. With your case, we're gonna do this shifting every cycle no matter what, right? Because here's the thing, it's not gonna repeat again till the sun's dead, no matter how fast you're running this. So what do I care if it's shifting all the time? It really doesn't matter to me. And then since you as a human are gonna take a long period of time, you won't get sequential runs out of it, so who cares, right? I would worry about this if you were pulling it large so you get overlapping chunks because somebody could get a long enough sequence to do it, but in this case you can't. So just by limitations of the human interacting with it. And like I said, you're not gambling off this, so who cares? Do we feel good with the basic idea? So this will be a very simple one for us to generate. All right, that's all I'm going to say for that, then we'll just walk through the code. Okay, so we good? Otherwise I'm going to erase and move to the next section. Okay. The other thing you need to worry about is how to generate some of these components inside of the design. One of them is you have to be able to output from here. Right? So we've got a 7-segment display. I asked if everybody remembered, but let me just make sure that everybody does. Right? Can somebody tell me wiring-wise how this is hooked up, my 7-segment display?
Four anodes and the cathode for each part.
Okay. So I've got 4 anodes.
So hooked up in a
And how many cathodes? 8. All right. So, what are my 8 cathodes? A, B, C, D, E, F, G, and D, P, decimal point. Right? Those are the 8 ones you're going to use. Of those, we're not going to use decimal points, so don't worry about it. Right? So, every single one of my D's are all hooked together. Right? So, if I were to look at this, this right here is actually an LED. Right? So, if you get current flowing through this, it's going to light up for me. So I hook all of my ones together, and I have to hook them to ground. So I do this. Why do I not do this?
You don't want them all to light up at the same time.
But they won't all light up at the same time. But this, so this part here is actually what I do. The problem in what I've drawn is here. So we're going to handle not making them all light up at the same time by handling the other side, the positive supply. I need a resistor. Why do I need a resistor?
Current limited.
Yeah. Otherwise, I've got 3.3 or 5 volts running across this little diode, which is going to take, depending on whether it's germanium or silicon or whatever, it'll be anywhere from 0.3 to 0.7 volts, somewhere in there as a drop, which let's say it was 3.3 volts, and let's say it was germanium, right? So it's 0.3 volt drop. That means I got 3 volts over essentially no resistance. The current's going to spike and that LED will burn out. So this is actually built into your board. They have a little resistor, which is a current limiting resistor. But this is still not what happens. So that's the first thing I need. So this is going to become an I/O pin. If I write 1 to it, guess what happens? Yeah, because now it's high, there's no sink. So it doesn't matter what voltage you put up there, even if you give it power, it's got power here, there's no current flow. So to turn these on, you have to give it a 0. So you give it, this is why this one is important to understand. You give it 0 to give it a ground. So if you write 0 to the anodes, you have supply to ground, right? This will limit the current, so I'm capable of sinking that current, and now you're good. That make sense? All right. So we've handled the first part. And imagine this thing is repeated for every other one of the things. I don't have any power to this thing yet. So now the question is, how do I get power to it? Well, if I just powered all of these, what would happen? I'd have 4 identical ones. So is that good? No. So I don't want that to happen. So I need to be able to turn each of these on individually. All right? Now, how can that work? If I turn one on, then the next one would blink? It will blink. Right? Of course it's going to blink, but when you turn this one on, it'll take a little while for the light to drop off, and if I do it fast enough, your eye can't respond quick enough. Right? Because you see light by a chemical process in your eye. Right? Light comes in, and it takes a chemical in your eye, and it converts it to a different form. Right? And then your eye measures the quantity of that chemical, and it interprets an amount of light that came in from that, and it will then signal the brain. And it doesn't instantly flip back. So if you've ever gone outside and you looked up and, saw something bright, and you still see the shape of that thing for a while, that's because those chemicals are still converting backwards. Right? There's a decay of the chemical reverting back to its original form. That's why you see that spots on your eye. Right? So your eye is going to smooth this for me. Your eye is a low-pass filter. So if I blink this fast enough, there's a little delay before the light will drop off here, which is a little bit of a low-pass filter. Your eyeball is a low-pass filter. So as long as I get it down in the 1 to, say, 15 millisecond range, somewhere in there, right, you will never be able to tell the difference. So we're good enough. So I just have to switch quickly. I can easily do that. A millisecond is slow to me. So no worries there. I'm going to hook all of the powers on this one together. Right? So I'll take all the power sides. Maybe I'll do this in a different color. Take all the power sides and I'll hook all of them together. Power side, power side, power side. All right, so I'll hook them all together. And there's the line for my power. So that when I supply power, I supply to an entire one. And I do that same thing to each one, so I can turn on this one, or this one, or this one, or this one. So if I supply power here, and I supply ground here, I'll only light up the appropriate ones on here. Does that make sense?
When you say the appropriate ones, why does it not light them all up?
Because not all of them will have grounds. If you don't supply ground to C, but you do to D, then I'll have, voltage here, and I'll have voltage here, so no current will flow, so no light. but you'll have voltage and ground, so you'll see light. So only where you see voltage on the one side and ground on the other are you going to see light on. And you can control which ones get ground by this side, the cathode side, and I can control which ones see power by the anode side. So let me ask you, can I do this? And then just give it a 1 to turn it on. How many say yes? How many say no? Now, I got around 60% of the class. So 40% of the class is not voting here, right? So here's my thing on voting. I don't care what your answer is. Won't remember. Neither will your friends, right? You want to think about it and commit to something. And here's why. It's actually for your own brain's learning. If you commit to it, you're right, you're like, yay, right? So you get a happy experience. If you commit to it and you're wrong, your brain goes, I've got to learn, I didn't know something, it'll release learning chemicals and you'll learn. If you don't commit to it, you're like, yeah, I would have picked that, right? And you learn nothing. Right? So it really doesn't matter which one you pick as long as you commit to it strong enough that you personally feel it, right? And then afterwards, either celebrate or go, I'm going to get this, right? Either one of those things is correct in the appropriate locations and it'll work to your benefit, right? So that's why the question's there, is just really to trigger the learning chemicals when needed, right? So let me try one more time because I want 100%. How many people say I can do this? How many say I cannot do this? Okay, I cannot do this. Why? Okay, I need a resistor. But, well, actually, let me put the... I would need a resistor protecting here. Now, if this is my only setup, that resistor would be covered by this resistor. But I will actually need a resistor here. So I'll grant that as an okay thing, but technically I've got enough resistance here to protect me. So there's a deeper reason why I can't. This is an output of my system. As an output of the system, it can supply a maximum of 1 pin's worth of power, which on most of these output gates for our systems, it's a low voltage setup, which means you're somewhere less than 20 milliamps. That is going to have to flow through 8 devices. This is called the fan-out problem. That means each one of these devices, if they're all turned on, is going to get 20 over 8, or about 2 milliamps, which is not going to be very bright. So what that would mean is that as you started getting more of them lighting up, less ones would be brighter, more ones would be dimmer. That's innately unsatisfactory. And it's just because this pin cannot supply enough current to do it. So I need to connect directly to my power rail, and that's why I need this. So now I've got a power rail, and I have to be able to switch that power down to here. Do we have a device that can switch power? A transistor. So this brings up that age-old question of which transistor do I want? I'll just draw generic. Now I haven't specified PNP or NPN, but it makes a difference. It does. So PNP versus NPN, one does a really great job of switching power, the other does a great job of switching ground. The question is which is which. NPN does ground. Think there's more N, so it's negative, right? PNP switches power. So I want a PNP, right? Now, since I want a PNP, to open this switch, what has to happen? I have to bias this diode. If you get this biased, right, it will open up this gate and transition things down. So in other words, if current flows here, current flows here. It's another way of thinking about that. Right? So what value do I have to put on this pin to get current to flow? A 0. This always confuses the heck out of people when they go to write it. They're like, well, okay, great, that makes sense. I put a 0 to give me a ground. Why is it I do a 0 to give me power? You're doing a 0 to bias the transistor so it opens the switch. Okay, so if you're wondering why am I in a digital class giving you an analog circuit, it's because if you don't, you have no idea what value you're giving. So don't tell this to Charlie, right? But if you don't understand both sides, you really don't understand what you're doing. Right? So, you know, I'm sure I'll hear back from you at some point on that. But it is actually a very true statement. You need to understand the entire picture of what's going on. So hopefully this makes sense. When you look at the diagrams for these, they'll give you circuit diagrams. If you look at the circuit diagram, you'll understand your system, and therefore you'll know how to interface it. So this becomes very important. So I write zeros to turn either, which means a 1 turns both off. That make sense? Okay. So that should be all you need to know. Well, let me do this. Now I need to be able to switch between them at a reasonable pace. So that means I need to find some way to get this in about the millisecond range. So what you need to know, anybody know a way I can figure out how long a millisecond happens?
Look at the clock cycle.
Okay, I get clock cycles. My clock cycles are happening in the megahertz range. On ours, I believe it's 100 megahertz. But a lot of FPGAs are anywhere from 20 to 100 megahertz. It's pretty standard ranges. You just look at the clock timing number on them. I believe ours is 100. Right? Not as big, you just look it up in the spec sheet and away you go. Right? But we want to get to the millisecond range. So if I'm at 100 megahertz, how long is a clock cycle? 1 over 100 megahertz, which is about 10 nanoseconds. Right? So I get that ratio. So it basically takes 10,000 counts to get there. Right? Actually, 100,000. Right? Sorry. Right? So 100,000 counts will get me to a millisecond. Because 100 gets me to a microsecond and then another 1,000 to a millisecond. So I need somewhere in the range of 100K as a counter. How big of a counter to get me 100K? How big of a counter to get me a K?
10,
2 to the 10th.
19,
Right? How many if I want 1,000,000? This is 1K.
100,
2 to the 20. Right? So if I want to go between, so I know it's somewhere between 10 and 20 bits, right, as my counter goes. Now all I have to do is 100. What is 100 log 2?
840 double. Yes, 8.5.
2 to the 6th is
Oh,
64. 2 to the 7th is 128. So you're 6 point something. Right? So here's the big question. You're either going to do 2 to the 16th, 6 plus 10. That'll give you 64K. Or you're going to do 2 to the 17th. That'll give you 128K. If you do 2 to the 17th, it's a little slower. Right? If you do 2 to the 16th, it's a little faster. I'd probably pick 2 to the 16th. Right? That'll give you a little under a millisecond, but who cares? You're in the ballpark range. Right? How many of these do I have to switch between? 4. So imagine I took that 16-bit counter, right? That'll get me to around my millisecond zone. And then I want something that's going to switch roughly every millisecond. So if I've got 16-bit numbers here, and I peg 2 more on the left, the highest bit, right? 2 more bits here. You'll have to count all the way through these 16 bits till they're all 1, 1, 1, 1, 1. I add 1 more, it'll toggle this bit. So this will be 0 for an entire run of 16 bits. And then another run of 16 bits, it'll become 1. Then for another run of 16 bits, it'll become 2. Another run of 16 bits, it'll become 3. Another run of 16 bits, it becomes 0 automatically again. Does that make sense? All right. So all I need then is an 18-bit counter. And I'll output the last 2 bits, and that'll become the selector. That make sense? So that's what they do. So you just build a counter. Every clock cycle just adds 1 and writes it back to that number. Well, it's a pretty simple one, right? It's a 18-bit flip-flop, and there's an adder, right? That takes 18 bits from the state, adds 1 to it, and gets next state. And then as long as it's not a reset, it just adds it, and it just overflows all on its own. Now, you can also set a number where you decide to trigger them, right? And you can just, check to see if it's over this amount, you can do something with it. I personally don't like that, although you can. Partially the reason I like this is because it's just really robust. There's pretty much nothing bad that can happen. It's a very simple, just add. You can usually get to the ballpark zone pretty well. If you really need it that precise, that I don't want 64, I want 50,000 instead of 64,000 for the recount. Then I'd have to have a separate 2 bits. And I'd have to have my 64, and I'd have to check, or the 16, which is my 64, and I'd have to, look to see when this 64 is equal to 50,000 or whatever number you're looking at. And the second it's equal, I reset to 0 and send a toggle to this next one. I could do that, but you got to ask yourself, is that 14,000 really worth it? Maybe it is. For some applications, it might make sense. Right? For this application, I don't think it makes a lot of sense. I think you're better off picking between the 16 or the 17, and you're probably good enough at that point. Because all it'll affect is how bright or dim your LED looks. So if you don't like it, let it sit for a little while longer. That make sense? All right, so that's the whole idea of the counter. So it's just going to be an add 1 type of thing, and we'll just do automatic rollover. But they have their own one within the code, and you can borrow it. This idea of using a counter to downgrade, to slow down a signal, is going to be really important, because guess what? That's the same thing you do with a stopwatch. Right? You're just going to build a counter that's going to make a tick, right? That happens, every 10th of a second or whatever you want on your counter. And it'll send a counter, and then you'll have a series of digits, say 3 or 4 or whatever digits you want. And it'll send it. So again, it's just a counter, and you just got to pick it to the right time zone. If you're trying to correlate it very accurately to a fraction of a second, that's when it would make sense to do one of those if, because you might find out that 50,000 is the right number or something. And you don't want the 10% error. You don't want a 10th of a second becoming an 1/8 of a second, because you'll get drift in your stopwatch. So that's when it would make sense to do the if, would be on those. If you're generating an actual corresponding to a physical constraint, now it makes sense to precision tune that. Good? Okay. Now, here's my next comment that's on here. Let's think about our code. The book has a full set of code for a stopwatch. Within the book, which means you can also go to the website and download the code for a stopwatch. How does a stopwatch work? Button to start the timer for it, you have a button to stop, and it should hold the value. Within this thing, you have code to light up a 7-segment display if you understand it. It takes a number out from something and displays it on the 7-segment displays. How does this relate to your game?
Different parts that are necessary.
Yes, you can actually take the code from the book, the 7-segment display, and the stopwatch, and all you need is a clear state and then this random to when does it tell you to start going. So when you hit the start button, it doesn't immediately start counting, right? It will pick a random number and count to that, turn on a light, and then start the stopwatch. So you have a stopwatch plus one extra state. That make sense? So therefore, if you want to do this efficiently and you don't want to spend tons of time writing code, I would take their stopwatch, look at what their state is, and how to rewrite it. This is called code reuse. If you don't do code reuse, you will spend countless hours generating unnecessary things. To do code reuse intelligently, you have to be able to understand what they have and what you need and how do you polymorph them. Okay? Lots of people love to find code, but what they have to do is they have to find code that's basically exactly what they want. Right? I want you to learn how to be able to take previous projects and morph them. You'll get hired by some company initially and you'll do a bunch of projects for them. And most of those projects are going to look fairly similar, right? You're going to generate a widget that does this or a widget that does that, and there's going to be a lot of shared stuff between them. So if you learn, here's my basic format, and I can take that old project and I can modify it easy, you've got pretty tested, reliable code, which is nice. You're not just starting from scratch with all the errors that come with starting from scratch. You're also not just staring at a blank piece of paper. I don't care who you are, there's like this stop the second you're staring at a blank piece of paper. So getting something and modifying it, the only trick you have to do is make sure that you don't forget to do something. So this is where I think comments in the code work really intelligently. Is you take a look at what's there, you figure it out, you write out its flow chart. You write the no flow chart of what you want modified from there, and you mark what you want, kind of color them off so you can see them. Right? We sometimes call them red light. You highlight the ones you want. Right? You take where those things are, and you, in the code, you put a comment that says what needs to happen there. And you tie it back and give the name on that sheet of what it is. Right? And you give a single slash over that element, meaning I put the comment in. Right? Once you've slashed every element, you've put the comments in for every element. So you know what needs to happen inside the code. Now you go into your code and you take a look at those comments and you do what it says. Right? When you've done what it says and you're confident of it, put the other slash. Now you've X'd it out and you know you're done. So you can then kind of walk through your diagram and figure out you have now finished everything and you've got all the comments of what you modified to change the project. So if you did forget something, you can always go back to where the comment blocks are inside your thing to say, hey, this is what I modified, and if you forgot something, you can find it. Does that make sense? So that's kind of my suggestion of how to proceed with them. If we're good with this, I'm going to pull up the code and we'll talk about what the code looks like. Suppose I should be thankful. Now giving me all digital controls. I gotta see if this. Okay, hopefully that. It's a good job for anybody watching the videos later. Alright. So I just kind of wrote this one yesterday, just so we would have some stuff on here. So you notice I put a little comment block up top that told you I'm doing a linear feedback state register, Fibonacci style, 168 pseudo-random. I mentioned that the maximal poly is taking the feedbacks from tap 168, 166, 153, 151. Like I said, you can look these up online, and they just list them all. So I just looked them up. Those were the 4 taps I need. I mentioned here, don't forget to subtract 1, because our numbers are from 0 to 167. And when they list the taps, they list them from 1 to n, not 0 to n minus 1. So you have to do the minus 1 manually, otherwise you're not going to convert right. And I mentioned your key 1 through 4, so you don't have to do this. This is kind of like a fancy little addition I put onto it. These are the bits of pi. So 3.1, right? It kind of keeps on down. So this is actually the first, these are in 28-bit blocks, because 168 is 6 times 28. So you're going to have a seed you can set these on. And to make my seed kind of unique, I use seed and not seed. And then I combine my seed with each of these keys to just kind of make them all different. Now, in our case, it's utterly irrelevant, because by the time you start this and the time you read it, it will have gone through so much it won't matter. Right? I do suggest you do the seed and the not seed, right, because of this. Like for instance, since I'm only using 28 bits for the seed, because that's what's needed to make the 168 nice and neat, you can use switches to generate that. But what if somebody left all the switches 0? Then you'd have all 0 in your thing, which all 0 will always generate 0. So that's one of the things about these pseudo-random generators. You can never use all 0. It's the only number that doesn't go through there. Okay? So I have to have at least 1. So if I use seed and not seed, if somebody gave me a bogus seed, all 0s, the not seed will guarantee that it's not all 0s. So seed and not seed you can't get away with. And then if you wanted to start using your numbers right from the start, it would be a good idea to have some type of a hidden key that you combine them with. Now again, this is not a secure thing. So if you're using it right from the start, you probably need a different one. But I just kind of put this in because it's a standard trick that's done. So it kind of gave you some fun stuff. So you can actually not do this if you wanted to, but it's included just for usefulness. So seed, that's my seed for them. Whenever you hit the reset button, it'll load the seed. Right? Clock is just the regular clock, and the output is R. So I'm only outputting 1 bit at a time. So if you wanted to collect a larger number, you could just collect either sequential bits of R, or you could change this to a larger number and grab a chunk of my array. And remember, as long as you're sampling a long period between, you won't get sequential bunches, which is dangerous. We feel good? All right. So then all I do is I set, this is where the key part comes in, right? Logic 167 to 0, so this is my 168-bit shift register, state and next state. All right? So this will be the register, this will be the combinational logic. I make a 1-bit thing polynomial. Technically speaking, those taps are actually, it's a polynomial expression. So the mathematical formula for that, okay, I said I wasn't going to do this, but I lied. I do need one thing just to mention. When you do these taps, so the actual formula when you're writing this, for this one will be x to the 168 plus x to the 166 plus x to the 153 plus x to the 151 plus 1. That's the polynomial. And if you notice, these are the tap numbers. This is the one that's the feedback. So these ones are generating the input to the 0 spot in some sense. If that makes sense, right? And so that's why those taps are coming, and that's actually how they prove it. They prove that polynomial is a good polynomial for maximal length repeats. So that's how they get the mathematical proof of it, and then they can carry it back in, and that's where they come from. So this is from a polynomial, so I call it a polynomial. That's the whole reason to it. So I just have to calculate off it, right? I assign my polynomial, since it's a simple equation, it's a bunch of XOR gates, I just did it on an assign statement. There's no reason. You could do an always underscore comb, but why? Oh. So I just set it to be, remember we had to subtract 1. So the state for 167, 165, 152, and 151, and I XOR'd them together. There you go. That's it. So that's your calculation. And then my next state, right, that has to come in at the 0 bit. Now, since I've been doing all my other ones, putting the big number on the left, that means it's technically flowing this way from small to large. If you did 0 to 168, it would, of course, flow the other direction. So my small bit is on the right on this one. So I put the state, right, copied up here. This is the low 167, 0 to 166. The last one fell off the end, and the polynomial gets shoved in at the low end. And so every time that's my next state. So this just prevents me from having this ugly calculation over here. You could if you wanted to, but I also, that bit coming in is also the one I'm sending out. So this just made it easy for me to assign to 2 different locations. And then always, it's a flip-flop, clock and reset. If it's reset, then it was a pause edge of the reset, reset wins. So I insert seed, not seed, key 1 exclusive OR seed, key 2 exclusive OR seed, key 3 exclusive OR seed, key 4 exclusive OR seed. Right? So that mixes your seed and the key. Right? So that you get kind of a unique combination. So that's kind of the trick behind that one. If you don't want to use the keys, you could just put zeros being sent to those. Perfectly fine in this case, right? Because we're not going to use it for a long period of time. It'll have a lot of time to mix. When you look, the reason why I put this in, when you're doing it for your random, when you're simulating, there'll be a lot of zeros that are going to work their way through on the calculations, right, until it does it. So your simulation will have a lot of zeros if you don't do this at the very beginning. So you'll have to wait several thousand cycles before it starts looking good. And I didn't want to wait thousands of cycles before I got a good looking thing, so I just made a messed up key. So that's the reason for it. Otherwise, state gets next state in a regular clock pulse. That make sense? So if you look at it, this is a stupidly simple piece of code. Aside from the key mixing, which I actually stole from Feistel ciphers, so it is actually a thing from cryptography, but this is not crypto safe. But that's actually where I took the key mixing part from. Right. We feel good? So, this is one way, this is fully synthesizable. It's a flip-flop, simple polynomial calculations, away you go. Right? And when you simulate it, so you can do a real simple test file for this, just give it some, pick 28 bits as a seed to put in, give it a clock pulse coming to it, and just watch the output. And you'll see it'll mix up quite nicely. So, for a human being, you wouldn't be able to predict. And then you can decide if you want to expand this to slightly bigger. You can take, instead of doing polynomials, you could do state, 7:0 if you wanted 8 bits. Good?
So do we have access to these?
I will upload this to probably the Git, if that's cool with everybody else, GitHub. But I want to make sure you at least understood where it was. If you look at it, it's actually a pretty simple little bugger to use. But that'll make a nice addition to your code. All right, so that's the one the book does not provide explanation on. Let's start talking a couple things. This should be fairly quick going through. Okay, so here is their mod M counter. Notice they use parameters here, so default it's 10. For most of our stuff, you're probably going to want something more in the 16 to 24 range. Is usually pretty good. Typically somewhere around 20-something will get you to about a second range. You know, like 24 or something is often for a lot of these ballpark around it. All right, so you'll have to set the size of them, and then we'll have, of course, clock and reset. Right, the max tick that's getting set out, and I also am outputting some bits that are in here, right, for Q. So they set, so you get both of them, the tick that you can use to trigger stuff and also a number range. So this CLOG2 is actually a Verilog function. It came in 2005, just before, but it's also available inside of both 2008 and 2011 versions of System Verilog, which just does, this is just calculating our log base 2. Similar to, so the log base 2 function in C is called CLOG, because it's part of the C math logs. So that's all these are doing, is calculating from, you gave me a number range, I want to know how many bits to enumerate. So you're passing back base the number of bits minus 1 down to 0. So this is saying how big did you want M, and it's going to output. Then they just do the same thing. The reg itself and the next, this is going to be the memory, this is the next state logic. The flip-flop, you'll notice, looks pretty much the same almost every time we do it. You're going to get really used to this format. All right, that's your register, and then this is the next state logic. So what's this syntax? Question colon.
The ternary operator is basically an if statement.
It's like an if statement, but just automatically switches output. So the first one is the condition code. If it's true, it'll give me 0. If it's false, it gives me reg plus 1. So this is just your incrementing counter. It can infer from the plus 1. It can, well, from the plus, it can infer a counter. Right, and there's pre-built hardware for counters inside the system, so it usually infers one of those counters that's pre-built within the system, so you get a very nice fast circuit. So this is actually really good synthesis right here for our systems. And then it just sets the Q, and for the max tick, it just checks to see, right, does my RReg equal that M minus 1, which you got to pick its size, right? It's a mod M counter. So depending if it hits that number, then it outputs a 1 or a 0. So it's taking a look at that one and triggering. Does that make sense for a basic mod M counter? So it's going to do that count all the way up until you hit M. That M could be big. Right? So if you want a mod 50,000 counter, it's going to have to be fairly big, but C log of 50,000 is still not that big. It'll give you a 16. Because that could give you a 64. Good? So it literally is just going to check, it'll keep adding, and as soon as it's equal to, you know, if you were saying 50,000, once it's equal to 50,000 minus 1, it'll automatically roll over. And it'll just assign the 16 bits it needs to do that counting. So this is kind of a nice automated system. Does it have to synthesize this? Log base 2 calculation? No, it can calculate that one in advance. This is what's called static. So if before the run happens, it can use the parameter numbers to be able to figure it out, not a runtime data, but if it can use static data at the very start of the simulation, before the simulation runs, it will just do that calculation in advance and We feel good with the MODA encounter? So this is available to you. Does everybody have the code in the book? If you don't, if you go to the Canvas site, there's an announcement that says supplementary book code or something like that. And it has a direct link. Or you can pull up a web browser and you can go, if you type the author's name onto, and he's at Cleveland State, and you can go to Dr. Chu's books on his website, and you scroll down and you'll find our book. And then it has your available source code right here under source codes for, right, this is the basic book source code in a zip. You just click and download that whole zip, and it will give you every piece of code that's actually typed out in the book. So you'll get all these codes so you can modify them. So I have a direct link to this page inside Canvas, or use Google and search for function. There's also a bunch of other ones that are in here, but all this stuff below here is actually inside here. So if you download this, you get everything. This README is kind of a nice README. Other than that, it's pretty good. So you get everything you need there. Good? So all this code here that I'm showing you is freely available. All right. So the other one is this, for doing the MUX for the display. So you'll see here, remember I said 18? Ignore his comments. Like he'll give for different ones. Like sometimes he says 50, sometimes he says 100. Right? You might have to modify it to ours. I believe ours is 100. So you might have to change a bit or two here or there to make it increase. But again, same thing. Next, and a reg. The reg follows the exact same format. And it increments, right, because it's a counter. So what's going on with this?
So that's the,
Letting the display sequentially.
Yeah, he's taking those, remember I told you the last two bits,
Yeah.
right? So n is the number of bits, so the high two bits are n minus 1 and n minus 2. So he's taking the high two bits, and he's saying if there's 0, 0, right? Then he's saying, you know, the anodes, the first three are off, the very rightmost one is on, right? And then whatever you said the pattern was for the 7-segment display, it writes that to the 7-segment display. Right? If that pattern is 0, 1, it turns on the second one from the right. If the pattern is 1, 0, it turns on the second from the left. And just below this, if it was 1, 1, it'll turn on the leftmost. So it just walks through. And the counter walking through there will just automatically walk you through these. So for this one, this is why you don't want to play that up to a certain value, because it'll skew. The very last one will be around for a shorter period of time than the others. So the leftmost one will be dimmer. For these type of things, for outputting to a display, it has to be equal time on all of them to make them all equally bright. But that's really all they're doing here. And then you just have the different inputs. What's the display pattern for the 4 different bits? So if you look up here, right, he's got the 7-segment display. That's the output. Anode is an output. What's going on? You pass it the 4 patterns you want to display on the respective areas, right? And you send it clock and reset. And it'll pick which one of them should be displayed, i.e. the anode, give me power, and the appropriate one of these to be passed out to 7 segments at the same time. And then so in the master module, you would just instantiate this, hook those to the output, and this is from wherever you're generating the number from. So you would just have to make something that converts from your number to the 7-segment display. And they give you one of those as well. I believe it's actually in an earlier chapter, but you can look to see. Alls it is a case statement. That just takes the numbers and matches the appropriate 7-segment pattern for it, i.e. the anodes. So, pretty straightforward. Does it make sense? So from this plus a case statement to convert it, you now have a full driver for that. And you can use this for any setup. And then just take the stopwatch and go. So I dumped everything in here. I believe there's stopwatches in here as well, yeah. I'm going to ignore the display unit because they just took the display unit from here and copied it up. This is the part of the watch that does the driving of it. So it's got a clock, a go and a clear, those are your inputs, and then it outputs 3 numbers, because in this case the stopwatch only has 3 numbers. It gets the tens, the seconds, and the tenths of the seconds. I believe in the ones they do for this. And so they just do 3 different ones, and they make these decimal. So you just have to, you have a lower counter that is a tick to the tenths of a second. Once that reaches 9, when it goes to 10, you set it back to 0 and send a trigger to the next one up. So that's the trick behind this one. This right here, remember I told you might want a number to check that? That's the number that he's looking for. So he picks that one. I believe he picks that one because it's he's going off of a 50 megahertz. Right? So I believe that's going to be wrong by a factor of 2 for us, but you can double check. But if your thing is counting at the wrong speed, you can adjust this number. And then, you know, it's just, again, the 2 regs, right? He needs 23 bits to be able to count that high. If you have to go to 100,000, you have to add another bit. And then he only needs 4 bits to count a decimal number and the appropriate decimals. So when he gets to the flip-flop area, this is the counter to count milliseconds, and then you've got the other, your 3 decimal digits. Right? So for yours, since you're going to be doing a stopwatch, but somebody doing a random trick, you could just take this basic code. This will work great once the system has gone through its random count. It'll then trigger this code. It'll turn on a light, and now it'll start counting. And as soon as the person hits the stop button, away you go. So you can actually pretty much directly take this code, and just up above there was a start and a stop and a clear and all that kinds of stuff. A go and a clear. So the go button will just be generated from your random circuit, right? So the second they hit start, it'll have a counter for that one that'll count to a random number, right? And then when it hits its limit, it will send that go flag, and then it's done, right? It moves on to the next state. And now you're just in here. Right? So you can use a lot of this code. If you think about it, there's some nice stuff you can do so you don't have to write an awful lot. You should be able to pick my random thing. You have to make your own little counter, but you've got other counters to build them off. To just build a timer counter for that random part. And then force the states to go. Make sense? Do we feel good about the project? Oops. Sorry for anybody watching. Bumped the phone. All right, well, we're at our time, so hopefully that makes this, at the end of this, what I really, really want you to be is confident with just taking code, hooking the units together, how to mix and match, and to correlate it to hardware. Right? If you're at that spot, you'll be at a good spot when we start moving on to later sections. All right. As usual, if you have questions, let me know.